Okay, so 7.2, the normal distribution. So remember that the probability of a variable that falls within a range of values is equal to the area under the probability density graph for that range of values. So we're talking about probability distribution, so the probability of all the possible outcomes. Remember that. So in a continuous sense, it's always going to be the area under the graph. And remember also the area under the entire probability density is equal to 1. Okay, so it's because you're taking into consideration all the outcomes. All right, so we have a normal distribution. So many physical quantities like height and mass, they're distributed symmetrically and unimodally about the mean. Remember, unimodally means one hump. So around a mean value, you have a kind of bell-shaped curve that falls around its left and on the left and the right side. Okay, and this bell-shaped curve is a mathematical model known as a normal distribution. And this is so very often seen in so many different things, in nature, in measurements, in random things, physical quantities, like I said here, like height and mass. It's all normally distributed. Now, the normal distribution can be completely described by its mean value, mu, and its standard deviation, sigma. And the symmetric form of the normal distribution makes both the mode and the median equal to the mean. And the smaller value, the sigma, the more data cluster around the mean value, which is what you see here on this graph. And so you have a narrower bell-shaped curve. And if you have a larger value of sigma, then your values are more spread out from the mean value. So you have a more wider bell-shaped curve. Okay. Now, the normal distribution is standardized. Okay, so when we talk about the normal distribution, when we measure sigma values from the mean value, one sigma is this equivalent to a z-score of 1, and a z-score of 1 or 1 sigma above and below the mean value will represent 68% of all the data falling within that area under this curve. Okay, 95% of all your data is going to be between 2 sigmas, and 99.7% of all your data is within 3 sigmas. And anything after 3 sigmas is very, very negligible. Like you can see the curve continues infinitely in both directions on the left and right, but those values, those areas under the curve, those density values are very, very, very small. So most of them, almost all of them, 99.7% of them will fall between 3 sigmas above and below the mean. So let's do an example. Area under the curve. So Giselle is 168 centimeters tall. In her high school, boys' heights are normally distributed with a mean value of 174 and a standard deviation of 6 centimeters. So what is the probability that the first boy Giselle meets at school tomorrow will be taller than her? So remember, the probability is the area under the appropriate part of the probability distribution curve. So what we're looking for here is the probability let's try and fix that probability that Giselle's height of 168 centimeters would be less than the boy's height. Okay. All right, so how can we solve this problem? Well, let's look at what we're given in the graph. So sigma, the standard deviation is 6, and the mean value is 174. So it turns out that Giselle's height falls within the lower limit of 1 standard deviation away from the mean value. Okay, so if we said here 168 is equal to the mean value minus sigma. Okay, and we also know from up here that 68% of all your data falls between 1 sigma of the mean value. So 1 sigma, so the probability of the boy's height, x, being between 1 sigma below the mean and 1 sigma above the mean is equal to 68%. Okay, and this is true for any normally distributed graph. Okay, because this normal distribution is standardized. Okay, so it doesn't matter that we're dealing with boys' heights here or weights or whatever. If it's modeled by a normal distribution, then as long as you are 1 sigma below the mean value, then you can have, or above the mean value, 68% of all your data will fall within that. Okay, or you could say the probability that the boy's height is between 168 and the upper end, which would be 180, is 68%. Okay, so we're going to use this little fact to help us solve this problem, this first original, the probability that Giselle's height is less than the boy's height. Okay. All right, so how do I use this fact? Well, I'm going to divide the problem into two ways. I'm going to divide the problem, or this is the distribution curve that we're interested in, and this blue shaded area is the area that we want to calculate. Okay, so the probability that boy will be taller than Giselle is represented by the blue shaded area. Okay, so I can find that by looking at half of the 68%. Remember, the 68% represents the x between 1 sigma below the mean and 1 sigma above the mean. But if I just took 1 sigma below the mean, it's going to be half. 68 divided by 2 is 34. So by symmetry, the interval between 168 to 174 is 68% divided by 2, which is 34%. Okay, so I can model this problem, the probability that 168 is less than the boy's height. I can model that as saying, well, what's the probability that at 168 Giselle's height is less than, the boy's height's between 168 and 174, the mean values. What's the probability that the boy's height is between this little section of the graph, between the lower limit and the mean value? And then I can add the probability that the boy will be taller than the mean value. So the probability that the boy is greater than the mean value, 174. Okay, and we know that is 50%. Okay, 50% represents the graph of half the graph, the bell-shaped curve. Because this bell-shaped curve is symmetric about the mean values. So half the values are below and half the values are above. So I can calculate this probability now as 34% plus 50%. And total, that will be 84%. So therefore, the probability that a boy pick that that Giselle meets at random, okay, is taller than her would be 84%. I'm going to continue example number 2 in another video.